introduced this unit a couple of weeks ago. We said there was 4 properties of waves that were exhibited by electromagnetic radiation. One of those properties of waves was diffraction, and we defined that as the spreading out of a wave around a barrier or through an opening. We showed you a picture yesterday of actual diffraction taking place. Water waves that were coming towards this barrier, but this barrier that had a little opening in it. A little bit of the wave goes through that opening, and as opposed to bending, changing direction, changing speed, changing wavelength, none of that stuff happens. As opposed to that, the wave just spread out. It spread out around the opening. Now, we also said yesterday, if we happen to have not just one opening right here, but 2 openings, so another opening over here, then the wave would go through that opening as well, or at least a little bit of it would, and it would spread out the same as it did through the first opening. Now, 2 diffractions taking place, 2 spreading out waves taking place. At some point, those waves that are spreading out are going to cross paths. And as they cross paths, they're going to interfere with each other. When the crest of one wave meets the crest of another wave, we get what we call constructive interference. That's a big crest. When a trough of the first wave meets a trough of the second wave, that's constructive interference as well. It produces a bigger trough. But when a crest from wave 1 meets a trough from wave 2, then we get destructive interference. It cancels out. If we're dealing with water waves, the interference pattern would look something like this. You end up seeing, in some areas, bigger crests and troughs. Those are areas of constructive interference. But in some places, we see areas of smaller crests and troughs. In fact, calm water. That's where we have complete destructive interference. If it's water or some other visible wave, then we can see it by looking at it from above. But if it's light, we can't. The light must reflect off of something in order to see it. So if there's only air in this region where we see the water in the picture, there's nothing for the light to reflect off of. We don't see this pattern. It's happening. If we could see the light reflecting off of smoke or steam or something in that area, we would see something similar to what we see here. Areas of constructive and destructive interference. But most times, if it's just air, you see nothing there. If it's light, that is, because there's nothing to reflect off of. So what we do is introduce a screen over here. When the light reaches that screen, they will reflect. At this point, it reflects off of the screen and produces a bright spot where you have constructive interference. And at this spot, same deal. And at this spot, same deal. And at this spot, same deal. But in between those, because we had complete destructive interference, there's no light to reflect off of the screen. So we see a dark spot, the absence of a bright spot, the absence of light. This first bright spot, or this middle bright spot that we see right here, we're going to call our central bright spot, or our central antinode, or our central maximum, or our central area of constructive interference. And we're going to assign a number to our central number, or to our central maximum. And that number is going to be a 0. There is a maximum, or a bright spot, or an antinode, or an area of constructive interference on either side of it. We're going to call that our first order maximum, or our first order bright spot, or whatever. There is another bright spot to the left of the first maximum, and another bright spot to the right of the first maximum. We'll call that our second order maximum. And so on and so on and so on. It's not going to go to an infinite number. Okay, there is a finite number of maxima that we'll see, but usually it's going to go beyond a couple maxima or a couple antinodes on both sides. Now, in between the central maximum and the first order maximum, in between that, we have a minimum. That would be our first order minimum, but we're going to assign a number to that first order minimum of 0.5. Our second order minimum would be 1.5. And the same deal on the other side. First order minimum, 0.5, 1.5. You can see where those numbers come from, right? The minimum that's between the central and the first max is halfway in between. The minimum that's between the first and second maximum is going to be 1.5, right? Just a little bit of notation so that when we go to use our equations, it's going to make a little bit more sense to you. Finally, this is where we ended off yesterday. We had a graph of the intensity of the light that was reflecting off of the screen versus the position on the screen. So intensity on the y-axis, the position along the x-axis. We saw yesterday that we had in the middle this bright spot that had a high intensity. That was our central maximum, by the way, that we assigned a number of 0 to. And then we had a minimum. We call that our first order minimum, where there was no intensity, and we assigned a number of 0.5 to that. And then we had our first order maximum, which is the maximum that was right beside the central maximum. First order maximum, first order antinode, first order constructive interference, first order bright spot. We assigned a number of 1 to that. Second order minimum, 1.5. Second order maximum, 2. And so on and so on. And it goes on the other side as well. Now, I wanted to introduce a couple of equations. These two equations are not crazy hard to use, but the variables in those two equations are easily mixed up. They're not hard. It's just easy to mix them up from one variable to the next. So I've got that picture drawn once again, where we have our two openings, our areas of constructive and destructive interference, our bright spots and our dark spots. On this diagram, I want to label some of the variables or all of the variables in these equations. First of all, lambda. That's the easy one. Lambda is the wavelength of the EMR that's going through there. The wavelength of the light that's diffracting and interfering. It's going to be, it should be measured in meters, although you can get away with measuring it in other units as long as you're consistent. But unlike with the lens equation and the mirror equation, I strongly suggest that even though you can get away with other units, go with meters. By the way, a typical range for wavelength here is going to be 10 to the minus 7. It doesn't have to be, but it almost always is, because that's visible light. And if you're doing this experiment, you're almost certainly doing it with visible light. So you get a number for a wavelength that's not 10 to the minus 7, you're probably off. Not for sure, but you're likely. It's likely that you've made a mistake. All right, let's identify what little d is. It appears in both equations. Little d is this distance right here, the distance between the two openings, or between the slits. That's going to be a pretty small number. And it's going to be measured probably in meters. If you happen to use another set of units, just make sure you use the other set of units for all the numbers that measure distance. X, actually, let's go L right now. X is a tricky one. Let's go L. That's a lowercase l. By the way, when I write this equation on the board, I'll often write it like this, with an uppercase L. It's not that the uppercase L is better. It's just that if I write it by hand, and I write it with a lowercase l, you're probably going to get that mixed up with a 1, right? So when I write it like this, it means exactly the same thing as the way they write it on your data sheet. L, not a hard one either. L stands for the distance between the screen with the slits and then the detecting screen. So we'll say it's a distance between the openings or the slits and the screen that detects it. where you see the interference pattern. And once again, we're going to make that meters as well. Okay, here's the tough one. Here's the ugly one here. X. X can represent this distance right here. Let's do it in red, actually, where we see a little bit better. X represents this distance right here. Or it can represent this distance. Or X could represent this distance. X can represent the distance between any minimum or maximum and any other minimum or maximum. I hope all of you are thinking right now, that doesn't make sense. You should be thinking that doesn't make sense right now. How can we possibly get the same answer as the person next to us if X can be whatever we want? Okay, bear with me for a second and I'll explain that. For now, we'll just say it's the distance between max or min and max or min. So between one maximum or minimum and another maximum or minimum, whatever you want. Whatever you want. Now, probably going to use some distance that's actually given to you in a problem, right? But it doesn't matter what the distance is as long as it's measured from one max or min to another max or min. All right, we can do this if n is consistent with that. In this case, n would be equal to 1. In this case, n would be equal to 1.5. In this case, n would be equal to 3.5. Anybody tell me what n is based on what I've just told you? Christian was well on his way there. It's not the order or the maximum number, but it's the difference between them. Look, if you're going from the first max to the second max, 2 minus 1 is 1. From the central maximum to the second order minimum, where it's 1.5, 1.5 minus 0 is 1.5. If we're going from the second maximum on one side to the second minimum on the other side, 2 and 1.5 on opposite sides, the difference between them is 3.5. So we're going to say that n is the difference in max or min. And it's just a number. No units associated with it, it's just a number. So you can use whatever value you want for x as long as your value of n is consistent. That's how, even though you might use one number and your neighbor uses another number, that's how we end up getting the same answer. Because n and x, although they can be whatever we want, they have to be consistent with each other. Finally, there's one more variable here, and that variable is theta. Theta is an angle that's always measured from the central maximum to some other maximum. This could be theta. From the central maximum to some other max or some other minimum. Okay, that could be theta, that could be theta. It's kind of the same as x. It can be measured to whatever we want, to the second order minimum or to the fourth order maximum. But unlike x, it has to be measured from the central maximum. X can be measured from or to whatever we want. Theta can be measured to whatever we want, but it always has to come from the central maximum. The angle from central max to another max or min. And it's going to be measured in theta, or sorry, in degrees, of course. Now, just like with x, n has to be consistent. So in this case, theta is whatever, n would be 1. because it's the first order maximum in the central max. 1 minus 0 is 1. This one would be 1.5 because we're dealing with the central max and the second order minimum, which has a value, an n value of 1.5. 1.5 minus 0 is 1.5. So lots of stuff up on the board right now. It's not hard stuff, though. It's just a matter of keeping it straight stuff. And it is a little bit tricky to keep it straight right now. Okay, but conceptually, it's not actually all that bad. Once you start using it, it usually seems to come pretty well. One more tiny little thing. You notice here the second equation, big if after it. If dot, dot, dot. If what? Well, the first equation that you see up on the board there is always valid. The second equation is actually an approximation. It's never actually correct. But at small angles, it's very, very, very good. It's a good approximation. So good that they'll give you credit for your answer that you get from that equation on your diploma exam. But only at small angles. We want to be below 10 degrees Celsius. Sorry, below, not degrees Celsius. We want to be below 10 degrees. So if theta is less than 10 degrees, then we're allowed to use that equation. Sometimes you're not given the angle. Well, you can find the angle and see if it's less than 10 degrees. But if you do that, then why would you bother using the second equation? You might as well just use the first one if you're going to find the angle anyways. So I've got a little rule of thumb here. This rule of thumb is what we're going to use every time we want to try this equation. We're going to try this rule of thumb to make sure that we're allowed to use it. We want to check to see if L is greater than 10 times the value of x. So get the value of x, multiply it by 10, and see how it compares to the value of L. That's an easier check than finding the angle and seeing if it's above or below 10 degrees. If L is greater than 10 times x, this equation is fair game. And you know what? That's going to be the case 95% of the time. We always want to do the check, but 95% of the time it's going to work out for us. Now let's have a look at a question that's going to use one or both of those two equations that we just learned. Monochromatic light, what does that mean, monochromatic light? One color, mono, one chromatic color. Monochromatic light is incident on two slits that are separated by 0.3 millimeters. Even though I can use other units other than meters in these questions, I don't want to. I want to stick with meters, so I'm going to circle that, draw attention to it, remind myself to convert that to meters. The first bright fringe is located at 0.080 from the central antinode. That's a really small angle, right? That's significantly less than 10 degrees. That means that both of those equations that I learned, the one that was always valid and the one that's a really, really good approximation for small angles, they both work here. We're allowed to use either one of them. Depends on which one my givens fit the best. What's the wavelength of the light? Well, let's write down some givens here. My D, my little distance between the openings here, is 0.30 times 10 to the minus 3 meters. Yeah, I want to make it in meters. I can move the decimal place over, or I can just look on my data sheet and see that a milli is 10 to the minus 3. My theta here is 0.080 degrees, significantly below that 10 degree threshold for not being able to use the second equation. N is equal to 1. Now, be careful here. N isn't equal to 1 because they tell me it's 1 right there. N is equal to 1 because I'm measuring the angle from the central antinode, the central bright spot, to the first order bright spot. This is not 1 because I'm dealing with the first antinode. It's 1 because I'm dealing with the central and the first. And 1 minus 0 is 1. Now, if I was dealing with the second and third, N would still be equal to 1. But if I was dealing with the second and fourth, then N would be equal to 2. We want to find the wavelength here. Remember what I said you expect to get for wavelength? Probably somewhere in the 10 to the minus 7 meters range. Let's figure it out. Two equations, both of which I'm allowed to use here. I'm probably going to go with that first one since I have theta, d sine theta over n. When I can, I like to go with this one because this is the one that's always valid. But remember, if you don't have an angle from the central maximum, you can't use it. It's valid, you just don't have enough givens to use it if you don't have the angle from the central max. D is 0.30 times 10 to the minus 3 times sine of a really, really small angle. Make sure you're in degrees here. Divided by n, which is 1. Okay, let's figure that out. 0.3 times 10 to the minus 3 times sine of 0.08 divided by 1. 4.19. 4.2 times 10 to the minus 7. Right in that range that I expected to see, right? Wavelength, visible light, 10 to the minus 7 meters. Is that okay? No real tricks to that except remembering what each variable is. Okay, remembering what n is, remembering what L is, remembering what little d is, and so on. Let's have a look at those three questions, please, on page 689. All right, question number 13.9 on 691. It says a student measuring the wavelength of light emitted by krypton gas directs the light through two slits separated by this distance in millimeters. We want to be in meters, so let's circle that. The interference pattern is created on a screen 3 meters from the slits, and the distance between the second bright fringe and the central antinode is 1.18 centimeters. What is one of the wavelengths of light emitted by krypton gas? All right, well, this is a diffraction interference problem, right? We call it Young's double slit experiment. That was what the experiment that was first performed was actually called. Two openings, light goes through it, Young's double slit experiment. This is a Young's double slit experiment problem. And when we have a Young's double slit experiment problem, we have really two equations that we like to use. Lambda is equal to d sine theta over n. Lambda is equal to xd over n times L. Let's write down some givens and figure out which of those two equations that I'm going to use here. D is 0.264 times 10 to the minus 3 meters. I'm going to say L is 3.0 meters. I'm going to say X is 1.18 times 10 to the minus 2 meters. I converted centimeters to meters. My N value is second bright fringe and central antinode. There's my central antinode. There's my second bright fringe. N is equal to 2 minus 0, which gives me 2. And I want to find lambda there. So it looks like I want to use this equation, lambda is equal to xd over n times L. I want to use this. It fits the givens. But remember, there was a big if by that one. We got to check to see if we're allowed to use it. We have to check to see if the angle is small enough, below 10 degrees, to use it. So my rule of thumb check, without having to do trigonometry, my rule of thumb check is this. Is L greater than 10 times x? If it is, we're good to go. L is 3. 10x, multiply that by 10, I get 0.118 meters. L is way bigger than 10 times x. Not just bigger, but it's way bigger. It means my angle is really, really small, certainly below 10 degrees, and I'm allowed to use this equation. So let's try it. We got 1.18 times 10 to the minus 2 times d is 0.264 times 10 to the minus 3. 2 times 3. Say 1.18 times 10 to the minus 2. 0.264 times 10 to the minus 3. Press equals. Now let's divide it by 6. 5.2 times 10 to the minus 7, which again is right in that range that I expected to get, 10 to the minus 7 meters. You don't get 10 to the minus 7, doesn't mean you're wrong for sure, but there's a very good chance you are. All right, let's have a look at page 691 now. All right, if you're not having any trouble with those questions, I want to take you back to the example for just a second, just to draw your attention to one thing that we didn't talk about when we did the example. The question says, what is one of the wavelengths of light emitted by the krypton gas sample? So if they're saying that what's one of the wavelengths emitted, then the inference is that there's more than one. There's multiple wavelengths. We used one. Let's assume for a second that we're shining green light on these two openings in the Young double slit experiment. If we shine green light, then this is the pattern that we end up seeing. We have bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. This would be our central antinode right here. This would be our first order antinode, second order, third order, first, second, third order on the other side as well. First order minimum, second order minimum, third order minimum, and so on and so on and so on. And it's exactly what we expect to get, right? Bright spot, dark spot, bright spot, dark spot. One color, because that's all we put through these two openings. But if we put polychromatic light or multiple colors through, then this is what we get. We still get a first order maximum, sorry, a central order maximum, which is a bright spot, which if we put multiple colors through, we combine all those colors together, it forms white light, and that's what we see in our central bright spot. But our first order maximum consists of kind of a rainbow, as does our second order maximum, and so on, and so on, and so on. Here's what happens. Just like different wavelengths refract at different angles, different wavelengths diffract at different angles. Red light refracts the least. Remember when we have the prism? We get violet light down here, and we get red light right here. Red light refracts the least. Red light diffracts the most. So we're not saying that each of these colors is a first, second, third, fourth order maximum. They're all first order maximum. There's a first order maximum for each of the colors. We can see that red light has spread or diffracted the furthest away from the central. Okay, it's opposite to refraction. Red light refracts the least, red light diffracts the most. Violet light refracts the most, violet light diffracts the least. It produces a rainbow, but it's opposite to what it was for refraction. Instead of Roy G. Biv, like we had with refraction, we have Viv G. Yor, right, as measured from the central maximum, Viv G. Yor, when we're talking about diffraction and interference. So how do you deal with this in a problem? Well, guess what? We already did. We were asked in this case for one of the wavelengths of light emitted by krypton gas. All I want you to do is treat it the same way. If you have multiple colors, then pick the relevant color and go with it. If you have data for this color of light, then use that color of light. If you have data for a different color, then use a different color. Don't treat this question that you see right here, question number 2, any different than question number 1. If you're given data for green light down here, then use green light. If you're given data for red light down here, then use red light. Don't treat it any different, okay? If you're given more than one color, pick the color that you have data for and pretend the other colors don't even exist. Like, given data for green light, pretend red and orange and yellow and blue and indigo and violet don't even exist. Just erase everything else and go with green. Make sense? Okay, one more example, then we're done for the day. Page 693, this one says a diffraction grating has 1,000 lines per centimeter. What does that mean? I don't know. We'll deal with that in a second. When light passes through the grating, an interference pattern is produced on the screen 4 meters away. The first order bright fringe is 19.2 centimeters from the central antinode. That's the wavelength and the color of the light. This sounds an awful lot like Young's double slit experiment, except that it's not two openings. It says that it has 1,000 lines per centimeter. So instead of having a situation like this, where we have an opening and then another opening like this, in a diffraction grating, we end up having hundreds or even thousands of openings like this. Here's the thing. The pattern formed, the interference pattern formed by this is bright spot, dark spot, bright spot, dark spot, and so on. The interference pattern formed by this is bright spot, dark spot, bright spot, dark spot, and so on. So we end up seeing, for all intents and purposes, the same thing with 1,000 lines or 1,000 openings per centimeter as when we have two openings. We just have to be able to deal with that number, that's all. Let's write down our other givens and then we'll deal with that number, all right? We have a screen that's 4 meters away. L is 4.00 meters. We have a first order bright fringe measured from the central antinode. That's going to be X, 19.2 times 10 to the minus 2 meters, or 0.192 meters. We're going to say that N, first order bright fringe, central antinode, N is equal to 1. We want to find wavelength. We also have something that's 1,000. That's not D, rather that's 1 over D. That's the reciprocal of D. So the first thing that I want to do whenever I have a question that involves a diffraction grating, it says lines per centimeter, 1 over D, is get D. Make sense what I did there? If I have lines per centimeter and that corresponds to 1 over D, then flip it over to get the value of D. Instead of being 1,000, it's 0.001 or 1.00 times 10 to the minus 3. Now I want that in meters, so I'm going to convert that to meters now. I get 1.00 times 10 to the minus 5 meters. And now I think I'm going to try that equation, that second equation, xd over n times L. Am I allowed to use it? Well, is L greater than 10 times x? L is 4. 10x is 0.192. L is way bigger than 10 times x. So sure enough, I'm allowed to use it. Okay, well, let's plug in our numbers in. 19.2 times 10 to the minus 2 times D, that's the number that I just got. Do this on the calculator here. 19.2 times 10 to the minus 2 times 1 times 10 to the negative 5. .8 times 10 to the minus 7. Right in that range that I was hoping to get. Visible light.